In this video, we'll look at physical properties of liquids and solids. Now that we've learned about intermolecular forces and the forces that hold our molecules together, let's start looking at how they affect the properties specifically of our liquids and our solids. So if we look at the property of liquids, that's related to the distance between the particles and also to the intermolecular forces. So the particles in a liquid are always much closer than they are in a gas. That's why we're going to focus on liquids and solids. And the liquid particles, they're not fixed in place. Remember, in a solid, your particles are locked in place. In a liquid, the different molecules flow around each other and start moving around each other. And so intermolecular forces plays a big role, particularly in our liquids and the properties that our liquids exhibit. First property we're going to look at is vapor pressure. And when we're looking at vapor pressure, that's when we're looking at the boiling point of a liquid. And so when we talk about the boiling point of a liquid, it's the temperature at which the vapor pressure is equal to the atmosphere pressure. And so if we have our container and we have our liquid in here, so what happens is some atoms or molecules have enough energy to break the intermolecular forces and move into the gas phase. And so we're having some of our molecules go from a liquid to a gas, but also it's happening because the atmosphere is exhibiting pressure on these liquids. Some of them in the gas phase are reverting back into a liquid. And so once we hit an equilibrium where the molecules going into a gas phase, going into the gas phase, and the molecules going from the gas phase back to a liquid equals each other, that's when we have our boiling point. So we can think of it when our molecules are liquid and they convert into gas. And then when it goes from gas back to liquid at the exact same rate, that's when we hit our boiling point. And so when we look at the normal boiling point, that's the temperature at which the vapor pressure is 760 torr, or 1 atmosphere. And so we can look at different molecules. We can look at diethyl ether, ethanol, and water. Diethyl ether is an organic compound, an organic solvent that has a structure like what's shown here. And so our diethyl ether, if we look at it and we think about which intermolecular forces exist here, I have mostly carbon and hydrogens, that's nonpolar, so I have London dispersion. I do have an oxygen that has 2 lone pairs. So a little bit of a polar bond here between the carbon and oxygen, and then more nonpolar. So there's a slight bit of polarity, but it's mostly just London dispersion. Compare that to something like ethanol, which has a structure shown here. So in our ethanol, we can see I still have that carbon hydrogens, just like my diethyl ether. But now the big difference, I have an OH. Whenever we see OH, your first thought should be there's hydrogen bonding. And remember, hydrogen bonding is a very strong intermolecular force. So I have a very strong intermolecular force here on this part of the molecule. Nothing like that exists in diethyl ether. And you can see the difference in boiling point goes from 34.5 degrees Celsius up to 78. So even though ethanol is a smaller molecule, because it does hydrogen bonding, the boiling point gets raised a lot. And then water, we know water can hydrogen bond even more. That boiling point's at 100. So what that means is diethyl ether has a very low vapor pressure. It hits equilibrium between liquid and gas, and between this happening at 34.5 degrees Celsius. So those molecules in the liquid phase, they have a much easier time breaking their intermolecular forces to turn to a gas, compared to ethanol, which has to break a hydrogen bond force. So that takes a lot more energy. That's why the boiling point is so much higher. And we can really look at how the different vapor pressures and how the vapor pressure is related to intermolecular forces. So if we think about our methane, CH4, that only has London dispersion, right? Carbon hydrogen, that's a nonpolar bond. So I don't have any dipole-dipole. I don't have any hydrogen bonding. So I only have London dispersion. Here with methanol, I have an OH. So I have London dispersion. We can see it's going to be a polar molecule if we draw it out. So I have dipole-dipole. And then I also have hydrogen bonding. Water we know is a very polar molecule. So it has our London dispersion. I have even stronger of a dipole-dipole and even more hydrogen bonding. So if we look at methanol and try and compare the amount of hydrogen bonds. Methanol is our CH3OH. So that oxygen there has one hydrogen that can hydrogen bond and two lone pairs. So it can make a total of 3 hydrogen bonds. And then if we look at water to compare, it has 2 hydrogens that can hydrogen bond and 2 lone pairs. So water we know can make a total of 4 hydrogen bonds. Since it can make 4 hydrogen bonds, that's why it has a higher boiling point and a higher vapor pressure. So you can see vapor pressure is related to the number of hydrogen bonds or the strength of the intermolecular forces. The stronger the intermolecular force, the more difficult it is to go from a liquid to a gas, the more energy it's going to take for that compound to convert from a liquid to a gas. So that's why those have much higher vapor pressures. So now let's look at another physical property of liquids. We'll look at viscosity. Viscosity is essentially the resistance to flow. So how much does that molecule not want to flow? Generally, liquids have a really low viscosity. Liquids are usually pretty okay flowing around and not having that much resistance to it. And now the ability of the liquid to flow, that depends on the size and the intermolecular force strength. So if you think about the water in your cup, water flows pretty easily. I mean, it's pretty viscous. If we compare that to something like glycerol, glycerol we see has 1, 2, 3 OHs. Glycerol is actually a very thick liquid. Glycerol we tend to think of as a very viscous type liquid. It doesn't want to flow that easily. And that's because if you think about it, we have 3 OHs here. I can make 3 different hydrogen bonds. I have 3 OHs that can make various hydrogen bonds. So it can make a lot more hydrogen bonds per molecule than water. So because it can make all those hydrogen bonds, it tends to not want to flow or move, because if the molecules are moving around, they have to break the hydrogen bonds to flow. So that's why they don't want to flow, because they have to break it. And we can see how size plays a part here too, because we can see glycerol is obviously much larger of a molecule than water. Even something as large as molasses. So we all hopefully have heard of molasses, seen molasses. Molasses is a very thick liquid that we can buy to sweeten our foods. So molasses has a lot of sugar molecules. Sugar molecules are really large. Sugar molecules also have a lot of OHs present in them, which means we have a lot of hydrogen bonding per molecule. And so the larger molecules also kind of get tangled with each other, and that helps increase the viscosity, which is how we ended up with the Great Molasses Flood of 1919. And the Great Molasses Flood of 1919 is where a couple tanks of molasses holding thousands and thousands of gallons broke, and flooded the streets and actually ended up killing some people. And then one thing to note with viscosity, the more we heat up a liquid, the less viscous it gets. So if you were to take your molasses and you heat it up, it actually flows a lot quicker and easier. If you cool it down, then the intermolecular forces in the molecules get closer together and you get stronger intermolecular forces. So then it doesn't flow as easily. There's not as much energy in that system there. Which we kind of have this idea about flowing in heat if we think about lava or molten metal. Metal, when it's heated up and it turns into a liquid, if you keep heating it even hotter, it flows a lot easier. Even lava will start flowing a lot easier if it's really hot. So it becomes a lot less viscous. If you start cooling it down, then it doesn't flow as easily. So it becomes more viscous when you cool it down. So our next property we're going to look at kind of relates to viscosity. We look at surface tension. So surface tension is the amount of work required to increase the surface area of a liquid. And so our surface tension actually kind of causes the liquid and the liquid surface to behave like a stretched membrane. And so the greater the intermolecular forces are, the greater the surface tension. And then surface tension also decreases as temperature increases. So if your temperature increases, your surface tension is going to go down, which kind of makes sense because our molecules, they're moving around a lot more. They aren't able to keep that tension and keep kind of that stretched membrane behavior. So we have a lot less surface tension at that point. And surface tension is used in nature by different animals that can, quote unquote, walk on water. So something like a little spider here, it's manipulating the surface tension of the water to be able to walk on it. So you can see it doesn't put enough pressure at any one point in the water here to have a leg fall through. Now, if we take the water here and we warm it up, the surface tension will decrease. And then our little spider, instead of walking on water, will now have to start swimming in the water. And looking a little closer at the surface tension and what this idea is. So as we said, it's the amount of work required to increase the surface area of the water. So what's happening if we look at our water and we look at our molecules here, the surface tension tries to minimize its surface area. So our molecules down within the liquid bubble here, they have lots of intermolecular forces. They have lots of pressure from all sides. The ones at the surface here, they only have it from the bottom and from the sides. They don't have any extra pressure or extra forces being acted on them from the top. So since they don't have forces on the top, they don't like that. So if we think about our water molecule, it's hydrogen bonding all beneath it. The one down here has it all around. So this water molecule actually wants to pull down, is being pulled down towards the rest of the liquid here. And so these molecules here on the top, they're actually being pulled down. And so that means our surface molecules have a lot fewer molecular interactions than the interior molecules. And so what will happen is, say if you have a surface, your water might kind of start to bead up on the surface. If it rains, you might have water forming beads on like the surface of your car. And that's because the water molecule is wanting to create a lot of surface tension to minimize its area, so it forms a bead. If it warms up, it might start to spread out. But it'll still kind of make a little bead shape. On a cold surface, you might end up with more bead-like water spots. On a warm surface, they might be a little more spread out, a little more lower. And this is because the molecules at the top here, the molecules on the surface, are all trying to pull inward so that they can have more intermolecular forces acting upon them. In the warm molecules, we don't need that as much because molecules are moving around a lot quicker here. And then thinking about this tension and this interaction with the surface, that's where you start looking at capillary action. And so capillary action is the ability of the liquid to flow in a narrow tube opposing forces of gravity. So what happens is if we have our tube here, you would take it, put in water, some water would just start to rise up. And what's happening is the water is rising up the sides of the tube and kind of clinging to the sides of the tube as it's going up it. This allows it to essentially flow against gravity. And so what happens when it does that, we have more tension on the surface here than we do in the middle. So we end up with what we call a meniscus, where the water kind of bows downward. So this is how water can travel up a paper towel through what we call capillary action. It's also how it travels up in plants. Or if you ever went to the doctor and they went to draw blood, they can draw it up in a capillary tube. They'd prick your finger, get a little bead of blood, and they put a capillary tube that just sucks the liquid, looks like it just sucks the liquid up. And it's the capillary action that's actually making the blood or the liquid flow up the tube. So the smaller the tube, the more capillary action we can have. The wider the tube, the less capillary action. So the water would flow up less and our column would be not quite as high as if we had the smaller tube. And then looking at this meniscus. When we look at the meniscus, they can be two different shapes. Our meniscus can either be concave or convex, depending on the intermolecular forces. A concave surface occurs when the intermolecular forces between the liquid and the glass are greater than the intermolecular forces among the liquid molecules. So if we think about our water here, it makes a concave meniscus because it's a little bit higher on the sides than it is in the center. And that's because the intermolecular forces along the glass and the water here are stronger than just between the water molecules. The opposite, a convex surface or convex meniscus, occurs when the intermolecular forces between the liquids and glass are less than among the liquid particles. So mercury actually makes a convex meniscus. So it ends up being a little bit higher in the middle than on the sides. And so we can see, if we look close up, the mercury molecules actually don't really want to touch the sides of the glass. They don't want to interact with the glass. The water molecules, on the other hand, want to interact with the glass. So that's why they kind of start climbing up the sides to try and interact with it more and more. And then one thing, when we're ever in the lab, we always measure at the bottom of the meniscus here. Because as we saw from the capillary action, if I have a smaller tube, the side here is a little bit higher. So it's going to go up higher on the sides. But if we measure at the bottom of the meniscus, that gives us a more accurate reading, no matter the size of our container. And one last property I want to think about before we move on to solids. If we think about density, density is a mass per volume measurement. So density of different states of matter is related to the distance between the particles. That's why in a gas, our particles are so far apart, so it has a low density. Liquids and solids, in liquids, the particles are close together. But since they're flowing freely, there's still kind of little gaps. We still have little tiny gaps between the molecules here. So liquids tend to have kind of a medium density. And then solids, they're all locked into place. So solids tend to be locked into place and pack as tight as they can. That's why most of our solids tend to have really high densities. Oops, can't spell. So solids tend to have high densities. Now water is one exception. Water, when it's in a solid state, is actually less dense than when it's in the liquid state. This is how ice floats. If we didn't have this unique property of water, where water is less dense as a solid, we'd have a lot less life on Earth, and all the solid ice would always sink to the bottom of the ocean, sink to the bottom of the lakes. We wouldn't have an ecosystem down there anymore. And that's because when water freezes with really big holes in the lattice. So that's how water ends up being less dense. There's a lot less water molecules per volume there. So now looking at our solids. When we look at the properties of solids, the solid state is usually held together in a very specific location. There's no movement. So we have two different kinds of solids. We have crystalline solids and we have amorphous solids. Crystalline solids are very well-ordered solids. You can think of those as kind of crystals that we normally see. Amorphous solids lack irregular form, so they're kind of just thrown together all hodgepodge. Glass is a good example of an amorphous solid. So if we actually look at the structure and look at these two a little closer, our crystalline solids occur when a liquid solidifies slowly and allows for the particles to become well ordered. Most solids we see in the world or we see in nature are actually crystalline solids. And it results from a symmetrical arrangement. Amorphous solids tend to occur when the temperature of the liquid drops rapidly. And so that results in particles that are going to be disordered. So they're somewhat randomly arranged. And so since they lack a regular form, you don't have these planar faces. So if I took a crystalline solid and I hit it with a hammer, it would actually kind of break right along one of the planes here. So it actually break right where the molecules are and kind of make a straight break. Amorphous one, we can't really make a straight line there. So amorphous ones tend to shatter. Crystalline ones tend to kind of break along straight lines. And so when we're looking at these crystalline solids, we say that they have a crystal lattice. So the pattern formed by the arrangement of those atoms or those molecules makes a crystal lattice. And so the atoms and molecules are always going to pack together efficiently to maximize their attractive forces and their bonding interactions. So they're going to maximize the intermolecular forces that they have when they pack together. And we have four main types of crystalline lattices and crystals that we talk about, or four main types of solids that we talk about. Our types of solids, we have metallic, ionic, molecular, and network. Metallic solids are usually our pure metals and alloys. So they're composed of atoms, and they do what we call metallic bonding. Ionic compounds, ionic solids, these are ones we've seen quite often. So they're ionic compounds and composed of ions, and they're held together through ionic bonding. Molecular solids, these are our molecular compounds, which are usually our nonmetal elements. So they're composed of molecules or atoms and really held together through intermolecular forces. So they're held together through the different forces we talked about before. And then finally, we have a network solid, which is composed of molecular compounds or nonmetal elements. And so that's when all atoms are covalently bonded together. So all atoms have covalent bonds that hold them together into one giant network. So when you look at our metallic solids, those are ductile and malleable. So if you think about your metals, you can usually form them into wires and sheets. The valence electrons move freely throughout all parts of the metal. So you can kind of think of it as your atoms are in a sea of electrons. And the attraction between the atoms of a metal are delocalized, so therefore it can move freely, and then the atoms can move freely when we apply a force. That's why they're so ductile and malleable. That's why you can hit pure copper or pure gold with a hammer and it starts to smash apart. And then alloys are when two metals are mixed together. So if we think about our pennies and think about our penny experiment, we have copper pennies. So we had pure copper pennies before 1982, right? Now we have pennies mostly made out of zinc and just a copper coating on the outside. Or if we wanted to, we can do a zinc coating and make a silver penny or a silver looking penny. If you take copper and zinc and mix it together, create an alloy, we have brass. So brass is just a mixture of copper and zinc atoms mixed together. And so we can create different alloys by mixing different metals together like this. Ionic solids, kind of ones we've seen throughout this whole class time. So they're composed of cations and anions, and they're arranged in a crystalline solid. So you can see here a sodium chloride. the sodium and chlorine atoms kind of arrange themselves. So I alternate between chlorine, sodium, chlorine, sodium, chlorine, sodium. So it has that alternating pattern to maximize the forces, to maximize those ionic forces. And you can have different arrangements. We have sodium chloride, we can have zinc sulfide, cesium chloride, calcium fluoride. All of these are different types of crystalline solids. And so they tend to have high melting points. They tend to be fairly hard and brittle. And then we have our molecular solids. Molecular solids are composed of molecules held together purely by their intermolecular forces. So the stronger the intermolecular forces, the higher the melting point for that solid. And so our nonpolar ones are held together just by their London dispersion force. So remember the example of the fatty acids, those were held together just by London dispersion force. Or you can think the butter you have, that stays a solid because it has a lot of London dispersion force, versus your olive oil has a lot less London dispersion force. That's why it's a liquid. Our nonpolar solids tend to be soft crystals, tend to have low melting points compared to the ionic ones. They do not conduct electricity and they do not conduct heat. So your polar solids, they're held together by London dispersion and dipole-dipole, possibly even hydrogen bonding. They tend to be harder than your nonpolar solids, have low to medium melting points, and they still can't conduct electricity. Finally, we have our network solids. Network solids are essentially a giant molecule. The atoms are held together by covalent bonds, so they're actually bonded together. With the molecular solids, it's just intermolecular forces. Here, it's covalent bonds. So an example that we all have heard of is a diamond. A diamond is a network solid. All the carbon atoms in that diamond are bonded together. Because they're all bonded together with covalent bonds, it becomes an extremely strong substance. It is very hard to break. It has a very, very stable three-dimensional structure. So because it's very hard to break, it's a very hard solid, we actually use diamonds to cut other things. And so if you've ever been in construction, they talk about a diamond tip blade. That way you have a blade that can cut through pretty much anything as long as it has a diamond tip on it, because diamonds are one of the hardest compounds we have. And it's due to this extremely strong covalent bonding across all the different carbon atoms. And so now we should know a little bit more about the physical properties of our liquids and our solids and kind of be able to predict some of these physical properties by knowing their intermolecular forces.